Hi, this is Mr. Kinzer, and we're ready to start part 2. Hope you all are doing well. If you did not first view part 1, please do so. It has the principle for science on it, and also some directions for taking and doing the homework and getting things turned in. So be sure to view that first, and then do part 2. Today what we're going to be doing is some review of work that we've already accomplished in class, particularly having to do with Chapter 10. In Chapter 10 we have a number of new ideas about solubility, and we went through that last week. In class, we went through a note sheet for Chapter 10, so be sure that you have received that Chapter 10 note sheet. And of course, I will be at the Hoffmantown Building D Tuesdays and Thursdays from, once again, 8:30 to 11 o'clock to hand out papers or receive any assignments that you have, including the literature and the history as well. So we're just kind of doing all of that as a convenience for you, and hopefully that'll work, that you could stop by Tuesday or Thursday. Well, let's take a look at some review. Now, we have had some great things. I love chemistry, and it's really fun to see how atoms work. And we know that the outside shell, or the valence shell of an atom, and the number of electrons that it has really determines how that atom is going to combine and what it's going to do with other atoms in making molecules. So if you remember your periodic table, I'm going to draw out a kind of for those 7 columns. We're going to leave the 8th column off, the 8th family. Those are the noble gases. There's the 8th one right there, number 8. And we know that that outside valence shell is completely full. So those atoms don't react at all. They're happy. They've got that outside. They've got the 8. With the octet rule, they've got those 8 electrons in the outer shell. So we're going to go ahead and give you this chart that we gave maybe 2-3 weeks ago in class. So we have this first group, which is the alkali metals, 1A, and of course we know that they only have 1 electron. That's why they're the 1A family. They have 1 electron in that outer shell, that valence shell. So what they're going to do is they're going to tend to lose the electron to another atom, so that they will have a stable shell of 8. So they are going to lose one. Now, when they lose an electron, they become a positive ion. So they have a +1 charge. Okay, so we talked about that, and that's really important to review that. Hopefully you'll get this really lodged tightly in your mind, because it's pretty important, particularly with Chapter 9 and 10. So the 2A group, the alkali earth metals, of course they have 2 valence electrons. They will tend to lose 2 rather than to gain 6 to fill that outer valence shell with 8 electrons. So because they lose 2, they have a +2 charge, and so we want to write that down. They will be +2. Then the third group, which is the boron family, that boron family is going to lose the 3 outer shell electrons rather than gaining 5, so they'll be +3. And so these are, of course, oxidation numbers, and that's what we studied a little earlier over the last few weeks, kind of reviewing it each week, trying to make sure that we understand that. Now we get to the 4A group, and this is that complex group. This is the carbon group, and they can either lose 4 electrons, in which case it'll be a +4 oxidation number. They can also sometimes lose 2 or gain 2, so that's going to be a +2, or they can gain 4 electrons to fill that outer shell. So they can have really 3 possibilities here with the carbon family. And then we have 5A family. They can they are going to have 5 valence electrons in their outer shell. They can have a number of things that happen there too. They can gain 3 electrons to fill that outer shell. They can lose 5 electrons, and they can have a +5. They can also have a +3, and on occasion, one of their atoms will act a little funny and give you a +4. So we mentioned that both with this family and with the carbon family, you have to be given that information. You will not know what an atom does. You don't know what that carbon oxidation number is unless I give it to you, so I will. But this is a kind of a variety there. Now, the 6A group, which is the oxygen group, of course has 6 valence electrons, and they will likely gain 2 electrons, in which case they are a -2, very often -2, probably most often that. On occasion, they can be a +4, and on occasion, they will lose the 6 to another atom, in which case they are now +6. But usually -2, usually -3 over here in the 5A group. And always 1, 2, and 3 in these first few groups, and then always in the halogen group, the 7A family, they are going to be -1. They're going to gain that 1 electron to fill the outer shell. They already have 7, so they are always going to do that, and they're going to do that very decidedly. They are aggressive. As you remember, fluorine is the most electronegative element on the chart, and so fluorine is a grabber. Fluorine will pull that 1 electron off another atom and then fill its outer shell. So it is very, very, very electronegative. So just remember that you really have to look at that valence shell, and you really have to know the oxidation numbers, except for carbon, that carbon family. And most always, the others end up being very regular. But that middle 4A family is an irregular bunch. So you have to be told what that's going to be. Now, we talked a little bit about why that is and the usefulness of it. So let's go ahead and use the oxidation number to figure out these combinations. So, for instance, if we had Sr strontium, and strontium is in that second family, and so it's going to have a +2 oxidation number, and you're combining strontium with bromine, and bromine, of course, is a halogen, and it's going to be a -1 oxidation number. So to get the +2 and the -1 to balance and equal 0, we're going to try to figure out this combination. We really need 2 bromines. So the 2 bromines now, I have a -1 for each one, and the -1 and -1 is equal to the +2. So now it's balanced, and it equals 0. It zeroes out. So we have SrBr2 is our element, or our molecule. So that's going to be strontium bromide. SrBr2. Okay, so let's do another one. See if you can do this one. I'll pause. You can put it on pause, and you can work on this one, okay? So let's do magnesium, and we're going to do chlorine. So how does magnesium combine with chlorine? Go ahead, see if you can work it. Okay, so magnesium is going to have, because it's in that second group, the alkali earth metals, it'll have a +2, which is its oxidation number. And I'd like to just mention again, the halogens are going to be -1. And so we're going to have 2 of those chlorines join in to give us a balanced, we balance out at 0. Okay, so it's going to be Mg, magnesium chloride. Okay, so let's do one more just for fun. Let's use a polyatomic ion that you guys have learned recently. Remember page 193, you've got to have that memorized. If you don't have that memorized, you're going to be hurting when it comes to tests coming up. So be sure to have that memorized. Okay, for this third one, let's look at aluminum and the carbonate polyatomic ion. And the carbonate has a -2 oxidation number. It's got 2 negatives. And of course, aluminum is in the boron family, so it's going to have a +3. Okay, it's in that 3A family. So the question is now, how many aluminums join up with how many carbonates? And we have 3 and -2. We have to select something that will balance so that we get a 0 out on the oxidation number. So if we have 1 aluminum, that's +3. If we take 2 of these carbonates, that's going to give me -4. I won't have +3. If I have 2 aluminums, then I've got +6. I've got -4 if I have 2 of these. So if I have 3 of these, that will give me -6. So if I have 3 of these, so let's write down, I'll have a -6 if I have 3 carbonates and a +6 if I have 2 aluminums. So I'm going to need 2 aluminums, and then I'm going to need 3 of these carbonates. And so we have CO3, 3. So make sure your 3 is shown clearly. 3 times -2 is -6, and 2 times +3 is +6. So these 0 out, right? These balance, and that's what we have. Aluminum carbonate would be what we call that new molecule. Okay, so now let's review a little stoichiometry. One of our favorite things to do is balance equations. So we want to balance the reactants on one side of the equation with the products on the other side, because the atoms on each side have to equal. And so we add up the atoms, and we do it that way. So let me give you a couple to practice with, and we'll see how you do with it. Okay, so this first equation here is iron plus oxygen gives me iron oxide. And is it balanced? Well, we only have 1 iron atom. We've got 2 over here. You can see pretty quickly it's not balanced. So the very first step that you take to balance or to do stoichiometry is you look for those diatomic molecules. And of course, oxygen is diatomic. So we're going to put 2 next to that. We also have other molecules that are always diatomic. They're gases. For instance, we have fluorine, and we have nitrogen, and of course oxygen and chlorine. hydrogen, all of those are always diatomic. So you need to remember those 7 that we've talked about in class and kind of memorize those, because that's your first step. So we've gone ahead and we make this a diatomic atom. So now we've got 2 oxygens over here, but we got 3 over here. So let's go ahead and just tentatively assume that this is a 3. We'll put a 3 in front because we can only change the what? Coefficients. We cannot go through and change the subscripts for the equation. So let's only change coefficients now. We've got 6 oxygens on the left, and we've got 3 oxygens on the right. So if we put a 2 in front of the iron oxide, now we've got 6 oxygens. Okay, so the oxygens are balanced on each side, but we have 4 Fe's, 4 irons on the right, and only 1 on the left. So let's go ahead and put 4 in front of the left side, and we've got 4 Fe's, 4 Fe's. So the Fe's on each side are balanced, and then we've got 6 O2s, and we got 6 O2s. So this guy is balanced. We're happy about that. Let's take a look at the second one. See if you can do this. I'm going to give you a second to look at it, and then we'll resume in just a minute. Okay, let's resume. We have methane, which is CH4 plus oxygen, gives us carbon dioxide and water. So we can see immediately our first step, of course things are not balanced. For instance, we only have 1 oxygen on the left with the reactants, and we only have 3 oxygens on the right in the products. So we know right away we're going to have to balance. So let's take a look at oxygen. Oxygen is diatomic, so we definitely want to put a 2, showing that it's a diatomic molecule wherever it appears. And now let's go ahead. There's no other diatomics. Let's see what we can do. So we have O2 on one side, and we have H2O and CO2. Well, let's just put a 2 in front of this O2. Now we have 4. We've got 3 on this other side. If we put a 2 in front of this, now we have 4. We've got 4 oxygens, 2 with the hydrogen, the water, and 2 with the carbon dioxide. So we're good on oxygens. Now, let's see about carbon. We have 1 carbon on the left and 1 carbon on the right. That's balanced. We've got 4 hydrogens on the left, and we've got 4 on the right. And then we already have these balanced, so we're good to go. We've got balance to that second one. So make sure that as you look these over in your notes and prepare, that you understand these real well, because stoichiometry will be on our next test that's coming up. Stoichiometry is really important. Okay, let's look at a couple other ideas from the chapter 10 that we went over in class, but I'd like to just mention and make sure that we understand what is. Okay, so this is a universal solvent. I want to make sure that we understand, and that's water. We need to know that water is a universal solvent. First of all, what is a solvent? Well, a solvent is something that's dissolved into. The solvent holds what is being dissolved. So if we have salt and we add it into water, salt would be my solute. That's the thing being put into the water, and then the water is the solvent. It is holding the solute. So in salt water we have that occurring. And anytime we have a solution, we have a solute and a solvent. And the solute is the thing that is the lesser. This is going to be the lesser amount, and the solvent is always going to have more mass, more volume, because it's holding the solute. And you kind of see that with salt water very well. Now, water is the universal solvent, because in water we can dissolve just about anything. Water is a dipole molecule, and so water can hold anything in solution. So in the ocean, for instance, it has dissolved. Every single element is floating around in the ocean, dissolved by the water there, from salt to gold to silver to just every element really that you find on the Earth's crust is dissolved. Barium, scandium, potassium, all these different elements are dissolved in ocean water, because water is the universal solvent. So it's important to know it's that way because it's dipole. It has a positive and a negative end, and so the water kind of arranges its own molecules that help it suspend and dissolve other molecules.